Connections and bracing configuration. This is a presentation that was made with the support of the American Institute of Steel Construction. And the idea is to give some background in order to understand some configurations related with connections and bracing. The information here is adequate for buildings that have about 12 stories or less. There is more information related to this particular presentation in the AISC library. This is the American Institute of Steel Construction, and most of the projects are from that particular library. What we'll gain from this presentation? We'll have a general knowledge of structural steel that we already looked at before. We will understand the different type of steel frames and connections according to the definition of the American Institute of Steel Construction. We will understand several types of connections used in structural steel frames, also different connection types and bracing systems. As we already know, steel have a lot of benefits, and one of them are that the steel can be used with a reduced frame of construction and the ability to construct in different seasons. Well, that obviously have an economical concept inside, because the time frame of construction, when it's shorter, it will also be cheaper. Steel also can make large spans and base size, and is the material most adequate when we have long spans. Steel is not convenient when the spans are very small. It also provides more flexibility to the owners. Steel also is easy to modify and to reinforce, different to other materials where that is not possible. It's lightweight. Therefore, the price of the foundations is smaller in comparison with other materials that are heavier. It's also durable, long-lasting, and it's possible to be recycled 100%. Some important elements that are unique aspect of steel are that usually the steel is fabricated off-site, like in a shop. Therefore, the erection is very fast. That will be convenient in the case of schedules, and the coordination of the parties, therefore, is very important in order to get all those advantages. When we have forces in a structure, as we know, the forces will be transmitted from the top of the structure to the foundations, and we will have like a path that will move those forces from the beams to the columns, and finally to the foundation. Well, the forces will act horizontally when we have like gravity forces, but also can act laterally when we speak about wind forces. And all these loads that are applied in the structures will be transferred in a system that is supposed to be resisting of all these loads. Well, the system that is resisting the loads is composed of several materials. The most common material is a rigid frame. Well, the most common is a frame, and there are several types of frames. And when we have a frame, we are speaking about something like a column, a beam, and a column. That is a simple frame. Obviously, we can have a frame of this type when we have cantilevers. And usually those frames are attached to another frame or are attached to the ground. The attachment to the ground is very important. However, when we speak about steel, those frames, they need to be rigid. If the frame is not rigid, as you already know, the frame will tend to move and do something like this. It will deform. For example, if we have a load in this side, and as we can look, one of the sides will like rotate. And that rotation happens because there is no rigidity in those points, in those joints. However, if the element is rigid, and that means that we have something like a connection that allow us to have a better rigidity. For example, we have our frame, and we have a joint here that is rigid, or we have a brace system, like an element that is going from one corner to the other, then will be difficult that this material move. Why? Because in order to move, as you already know, in order to be deformed like this, one of the elements, in this case, for example, this yellow one, will need to become longer. And the other element, for example, the brown one, this, will need to become shorter. You see, the dimension changed. And that is difficult if we have a frame. It will be also difficult if we have joints. When we have a building made out of concrete, we don't have that problem because usually concrete is much thicker. The material that is used is very thick, and there is a strong joint in this point. Well, there is an intrinsic rigidity. But in the case of our material steel, that doesn't happen. Well, the frame is rigid if we have something that make it rigid, like for example, a specific connection. In this case, we have a frame here, you see, that help to make this rigid. That can be a moment connection that will allow to have rigidity. Also, if we have a shear wall, that is a wall, for example, made out of concrete, that will be very rigid. If we have a chevron bracing, like this element here, or we have an X bracing, well, in this case, we'll be able that are structures that are stable and all the architectural needs are met. Well, braced frames are rigid structures, and we will be looking some braced frames here in the left side, and rigid frames or frames that are very well connected in the right side. According to the specification of steel buildings, AISC 1005, we have two types of connections. Simple connections, that is the one that we are looking here in the right side, that we already spoke about them. And in this case, let me go back. In this case, you have a connection that is only in part of the frame, is affecting only this area of the material. Well, an I-beam has three components, and you have these elements in the top and in the bottom, and you have the central area. Well, when you have connections only in the central area, the connection is not rigid because the superior part could rotate and the bottom part also could rotate because it's not attached, it's free in those points. But in the web area, and the web is this area here, is fixed. The other one is the moment connection. In the moment connection, look, we have connections up, down, and in the center. We already looked this many times, and this is something very important because as a designer, your engineer will tell you when you are designing the building if you need a connection that is rigid or not. And you may want Not to calculate the connection probably, but just to design it and understand what you exactly need. What happens with this kind of connections is that all of them have some rigidity. Simple connections have some rigidity, but are free to rotate. You can have some partial restriction until you have a full restrained moment connection. That is, for example, the case C and D, where there are full rigid. Well, what happens in this particular case is the following. We have a connection that only connects the web. We have a connection that connect the up and bottom areas of the beam. Same happens here. And those connections are not connecting the three elements, 1, 2, and 3. Whenever this connection is connecting all of them, it's like you have welding in all this area. And this connection E have, for example, welding, other connection with bolts and welding. And well, these two connections are rigid, full restraint. We have one example here of a simple connection where only the web member is connected. This connection is not possible to look completely here, but what happens is that we had here a piece of steel here, and that piece of steel is bigger and is welded. It's in the back of this particular side 1, and after is bolt there. We have again here a connection that is very similar. You see, it's welded in this area. Let me go back. Here is welded here. And from the shop, you have this piece already welded there with the holes, and in the moment that they are building, they put the bolts, and that became an element. This is called double angle connection because probably you have an angle inside A and one angle there in the back inside B. And this is an angle that is like an L element. Well, we can have here more examples of simple connections between elements. This is a shear plate connection. Sorry, let me go back. This is what is called a shear end plate connection because there is a shear at the end. This is an angle connection that I wanted to look before. This is a seat connection, but it's an angle that is mounted on one side with one leg vertical against the column. It's a stabilizer in the top that we can look here. This is a T connection. We have a WT section that is connected, I mean an I-beam that is connected to the supported member of the flange. Here we have moment connection. All the three members are connected. That is for rigid frames, are fully restrained, and it can be partially restrained. Here we have a fully restrained. All three members are connected. This is partially restrained because we have connection in the inferior part and in the web area. This is enough to transfer moments, but there is some kind of rotation in the superior part. We have here a bolted stem plate connection. What is that? We have a plate that is this element here. That plate has been welded to the I-beam in all this area. also the other side, obviously. And finally, there are some holes there that will be used to connect the material to the column. Look, in order to make this even more resistant, because this side of the material could bend, in order to eliminate that possibility that the column bend, they have some restraint elements there. There are some elements that has been located there, like additional steel, to eliminate that possibility. This is a welded flange connection with a complete joint penetration groove, like the weld will go on both sides and connect the top and the bottom of the flanges. Let me clear here. And we have a PR moment connection. It's like it's called wind only. Well, we have a double angle that is a simple connection that will transfer the vertical shear forces and will resist all the forces that are produced, for example, for a wind. Look how the flange is very small here in comparison with the superior one. Well, the inferior one, the part that is located here in the bottom, here, is for the wind only. Well, it's quite smaller in comparison with this one that is supporting the rest of the loads, like the weight of the building. We have here a top and bottom plate angle. Well, you can look that the superior part have an angle. Also in the bottom, we have an angle and we have a plate in the middle. The idea is that the shear end plates will be used to transfer all the vertical shear forces. That means that if we have a beam, and that is convenient when the beams are not so long, we have a beam and there are some forces there, and this is the column, for example, that is supporting that beam. Well, that will tend to have like a crack because it's short, will not bend, but it will produce some shear. I mean, the possibilities to have some bending like that are not so big because the material is short, but, for example, but there is a possibility that will break here. Well, that shear connection will attach them in order to evitate that. And we have rigid frames here where you have moment connections. That can work for some buildings where you cannot have diagonal bracing. What is going on here? For example, we have a building for offices and we want to connect all these spaces. Having an element like this maybe is not convenient. Well, the diagonal bracing will divide the space. Well, it will be better to don't have that diagonal bracing and instead have a rigid frame in those points. And obviously it will be connected also with the floor in a rigid way, like this column and beam will be stable together with the floor and the beam that is in the floor. Braced frame, for the contrary, in some moments is possible. If you have a wall divided into spaces, we can imagine that in this particular area, there is no problem because probably these two spaces are separate to have a wall there. Well, before building that wall, that can be a dry wall, for example, a wall that is not rigid and not structural, we can have these two elements that will create a frame. Well, diagonal bracing will create stable triangular configurations. It's the most economical method to resist wind loads in multi-story buildings. And some structures like the one here can have a combination of braced and rigid frame. Maybe in other places, like in the facade, we don't want to have that brace. Therefore, we make the connection more rigid, and that could work perfectly. Well, the combination can be convenient in many buildings. When we are doing the construction, making the construction of a steel building, pieces will tend to move because not all pieces are together. Well, it's important to have some temporary bracing. Well, those elements will allow to plumb up the structural frame and give some lateral stability until the moment that everything is complete. And when everything is complete, we can take out these cables because all the elements are already secure. Usually in brace frames, temporary bracing are removed after the final bolt up is complete. The building is bolted, and after it came a final bolt to try to secure all the elements, and then it's possible to remove those kind of elements. There are several types of framing elements. There are concentric ones that are very symmetrical, and they go when the center line of the bracing members intersect. Like, for example, X brace, X, chevron, single diagonals. That means that the particular brace is passing to the center, the axis in the middle of the column and the beam. That is a concentric one. Also, it's convenient many times to have those elements in some areas as X frames that will be able to work like a truss. In multiple floor buildings, for example, we can have one of the base that is braced, but probably we don't need to brace all of them. In this particular case, the center is very important because the three bases in the center are supporting more weight than the ones that are in the stream. Something that we already studied. Like this column is supporting this half and half of this beam. And the same happens with these three columns and these three beams. But this side is only support half. Well, this area 1 and 5 are not supporting so much weight. 2, 3, and 4 are supporting more. Well, if we reinforce the area 3, then we are in some way reinforcing also because we are next to them, 4 and 2, that are the two areas that are supporting more loads. Well, it's very important to determine the location of the bracing areas because usually not all the areas need to be braced. Let me clean here. And when we look here, another concentric one, you see the axis is passing just by here. Let me go back again, sorry. Here. As I was telling you, in this particular case, this area is the axis, and this axis is going to the center also of the column and the center of the beam that is in this point. Well, that's why it's concentric. We can also have some kind of chevron connections like the ones here, V connections, K connections. The K connections are diagonal ones. V are like a V, and chevron is the contrary. It's like an invert V. I'm sorry, let me go back. And the chevron connections are this one. They usually use two types of connections. The floor level is connected with a gusset plate, like the normal X brace connection, and after in the top part instead, the bracing members are connected to the beam girder and they converge in a common point. There are gusset plates that are such flat plates that are located in the beams and columns to connect them. Well, you can look here how it's going on. We have first this particular I-beam, top, bottom of the I-beam. The I-beam is reinforced with some elements that make it tough. There is a gusset plate that is this element in yellow color. And that gusset plate will be welded to the beam. And now we have a surface that is flat and in the same direction of the brace, and the brace is connected. And that will be the brace. Here is connected. Look, the axis of this one is not going to the same point of this one. Well, in this case, we have an eccentric brace. When the brace go to the same point, like here, for example, this one that I am drawing, then it's a concentric one. We have here the centrically brace frame that is not going to the same point. It's like a V shape. We have here eccentric diagonals are not going to the corner, a little before the corner. And well, we can look here that the brace frames can deflect, especially if we have the same kind of bracing. A building that only having one side brace chevron connections or moment connection will tend to do so. However, if we combine them, we have a bracing of one type and a moment frame in the other, will be more difficult to create this kind of deformations. Well, combining two systems will reduce deflection. This is a plot of the moment resisting frame alone, the brace frame alone, and the combined frame. Well, in few words, we have a building, and this building is 18 stories. And when we have combined frames, you see that the deflection will be in inches at the 3 stories, will be about 2 inches. And when the building have, for example, a height of 9 stories, the deflection with the moment resisting will be 6. It will be smaller for and something when we have a chevron or K bracing, and when we have combination will be a little bit more than 2. Well, you see, it increases the deflection, and we don't want so much deflection. We don't want the building to deflect because that is dangerous. Well, a combination is better. The worst is just a moment resisting connection. This presentation is part of the American Institute of Steel and Construction, and you have some references here. Thank you very much.